What if one of the most important innovations in the future of railways does not come from the train itself, but from space? For more than a century, railway safety has depended on one essential question: where is the train? Every signal, every timetable, every movement authority, every control center decision, and every safety system ultimately depends on knowing the position of trains with confidence. If we know where a train is, how fast it is moving, and which route it occupies, the railway traffic can be organized and operated safely and efficiently. If that information is uncertain, the entire system becomes uncertain. Traditionally, railways have solved this problem through equipment installed on or beside the track. Track circuits, axle counters, balises, signals, interlockings, and onboard odometry have formed the backbone of railway detection and control. These systems are proven, but they are also expensive, infrastructure-heavy, and difficult to modernize across large networks. Every kilometer of railway requires equipment that must be installed, powered, inspected, tested, maintained, and eventually renewed. This is where GNSS enters the story. GNSS, or Global Navigation Satellite Systems, refers to satellite-based systems that provide positioning, navigation, and timing information. The best-known system is GPS, developed by the United States, but it is only one part of a wider global family. Europe has Galileo, Russia has GLONASS, and China has BeiDou. Together, these systems make it possible to determine location, speed, direction, and time across most of the planet. In everyday life, GNSS is so common that we barely notice it. It helps us navigate by car, use smartphone maps, track deliveries, monitor ships, guide aircraft, and synchronize digital networks. But in railways, satellite navigation is much more demanding. A train does not simply need an approximate location on a map. For railway operations, position must be accurate, continuous, reliable, and trusted. In safety-related applications, the system must not only know where the train is, it must also know when the information may be wrong. That is why GNSS in railways is not simply GPS for trains. It is a deeper transformation in how railways may be monitored, managed, and eventually controlled. The basic idea is relatively simple. A train can be equipped with GNSS receivers and antennas that receive signals from satellites. These signals are processed by onboard equipment to estimate the train's position, speed, and direction of travel. This information can then be combined with other onboard systems such as odometry, inertial sensors, digital maps, and train control equipment. It can also be transmitted to a central processing system or control center, where it is analyzed and used to update the real-time picture of the railway network. In more advanced architectures, ground-based GNSS reference receivers can also be installed at fixed locations. These receivers help correct errors in satellite signals and improve positioning performance. This is important because raw satellite positioning is affected by atmospheric conditions, signal reflection, local geography, and interference. By combining onboard satellite data with reference stations, odometry, inertial systems, and digital track maps, the railway can build a more reliable picture of where the train is. To understand why GNSS is so interesting, it is useful to compare it with traditional train positioning. In many conventional signaling systems, the infrastructure detects the train. Track circuits use the rails as part of an electrical circuit to determine whether a section of track is occupied. Axle counters count the wheels entering and leaving a section. Balises provide fixed reference points to the train, especially in systems such as ETCS. Onboard odometry then estimates how far the train has traveled between these reference points using wheel sensors, tachometers, Doppler radar, inertial systems, or similar equipment. This combination works, but it has limitations. Trackside systems require a large amount of physical equipment. That equipment is exposed to weather, vibration, theft, cable failures, power supply problems, and maintenance constraints. On busy main lines, this investment may be justified. But on regional lines, rural routes, secondary corridors and low-traffic railways, the cost of modern signaling can become a serious barrier. GNSS could change part of this logic. If trains can determine their own position more accurately using satellite signals and onboard systems, part of the localization function can shift from the infrastructure to the vehicle. This does not mean that trackside equipment will disappear. That would be unrealistic. But GNSS could reduce dependence on some physical devices, complement existing systems, and make advanced signaling more affordable on lines where conventional upgrades are too expensive. One of the most direct applications is real-time train positioning. If an operator or infrastructure manager knows the location, speed and direction of trains in real time, it can monitor traffic more precisely. For passengers, this can mean more accurate information about arrivals, delays, and connections. For traffic controllers, it can mean better decisions during disruptions. For freight operators, it can mean improved tracking of trains, wagons, and logistics flows. For infrastructure managers, it can mean more efficient use of capacity and better coordination of maintenance windows. This matters because railway capacity is not only about how many tracks exist, it is also about how intelligently those tracks are used. If the control center has a clearer and more continuous picture of train movements, it can detect conflicts earlier, adjust train paths more efficiently, and reduce unnecessary waiting time. On congested networks, even small improvements in traffic management can have significant operational value. For freight rail, the potential is especially important. Freight trains often travel long distances through yards, terminals, ports, industrial sidings, and border crossings. Their movements are less visible to the public, but they are essential for logistics chains. GNSS-based tracking can improve visibility by showing where trains and wagons are, how they are moving, and whether delays are developing. This can help terminals prepare for arrivals, customers plan loading and unloading, and operators coordinate international freight corridors more effectively. Another important application is safety supervision. GNSS can help monitor whether a train is where it should be, whether it is moving in the expected direction, and whether its speed is consistent with operational limits. When combined with digital maps and train control systems, GNSS can support geofencing, movement monitoring, and work zone protection. For example, a system could detect if a train is approaching a restricted area or moving unexpectedly. These functions may not immediately replace traditional signaling, but they can strengthen situational awareness and operational safety. The most transformative application of GNSS is its potential connection with ETCS and ERTMS. ETCS, the European Train Control System, is designed to provide a common train control standard across Europe. It is part of ERTMS, the European Rail Traffic Management System, which aims to overcome the fragmentation caused by different national signaling systems. ETCS already uses onboard equipment, balises, radio communication, odometry, and train protection logic to supervise train movements. GNSS could support ETCS in two main ways. The first is as a complement to odometry. Today, odometry estimates the movement of the train between known reference points, but it can accumulate errors over distance. Balises are used to reset or correct position. GNSS could provide an additional source of position and speed information, improving the quality of onboard localization. In this role, GNSS does not replace ETCS, it strengthens it. Future railway communication will also be essential. Planned systems such as FRMCS, the Future Railway Mobile Communication System, are expected to provide the digital 5G communication capacity needed for advanced railway applications. GNSS can generate positioning data, but that data must be transmitted securely, processed quickly, and used by signaling and traffic management systems. Without reliable communication, satellite positioning cannot become part of a truly digital railway. The second possibility is the use of virtual balises. A physical balise is a device installed in the track that transmits information to the train when the train passes over it. A virtual balise is different. It is not a physical object, but a digital reference point defined by geographic coordinates. When the train's onboard localization system confirms that the train has reached that point, it can trigger information equivalent to what a physical balise would provide. This concept is attractive because it could reduce the number of physical balises needed on the track. That could lower installation and maintenance costs, especially on regional and low-density lines. But it also shows why railway GNSS is technically demanding. A virtual balise is useful only if the system can determine with high confidence that the train has reached the correct location. On a simple open line, this may be easier. In a complex station area with parallel tracks, switches, platforms and overhead structures, it is much harder. The system must know not only the train's position, but also the exact track it occupies. This is why railway GNSS must deal with four key concepts: accuracy, availability, continuity, and integrity. Accuracy means how close the estimated position is to the true position. Availability means whether the system can provide positioning when needed. Continuity means whether it can continue without interruption. Integrity means whether the system can detect when the position information is unreliable and warn the railway in time. For safety-critical rail applications, integrity is just as important as accuracy. Over the last 2 decades, several European and space sector initiatives have studied GNSS for railway applications, especially in connection with ERTMS and ETCS. Projects such as Gadaros, Integrail, Rune, Locoloc and Locoprol explored different approaches to GNSS-based localization. Their approaches varied, but many conclusions pointed in the same direction. GNSS has strong potential, but it must be integrated into a broader redundant system. Testing has included laboratory work and real-world trials. Laboratory testing allows engineers to simulate satellite conditions, test onboard equipment, and analyze system behavior in controlled scenarios. Real-world testing is essential because railways contain conditions that cannot be fully reproduced in a laboratory: tunnels, bridges, stations, vegetation, curves, mountains, urban areas, and complex junctions. Institutions such as ADIV, CIDEX, and INICO have participated in European innovation projects testing satellite technology for rail, including concepts such as absolute positioning, virtual balises, and train awakening. For specific project status and certification progress, the latest sources should always be checked. The biggest challenge is the railway environment itself. Tunnels block GNSS signals completely, mountains and deep cuttings create shadow zones. Station roofs, overpasses, dense urban areas, and natural obstacles can weaken or interrupt the signal. In cities, signals can reflect from buildings and structures, creating the multipath effect. This can distort the calculated position. On a road, a few meters of error may be inconvenient. On a railway, a few meters can place the train on the wrong track in the digital system. There are also deliberate threats. GNSS signals can be jammed, meaning they are blocked or degraded by interference. They can also be spoofed, meaning false signals are generated to mislead the receiver. For normal navigation, this may be inconvenient. For safety-critical rail applications, it can be dangerous. Therefore, GNSS-based railway systems must include interference detection, cybersecurity protection, fallback modes, and alternative positioning sources. Standardization and regulation are equally important. Railways are cautious with safety-critical innovation for good reason. Before GNSS can be used for signaling functions, it must be specified, tested, certified, and accepted by regulators and operators. But the conclusion must remain realistic. GNSS will not replace all railway signaling equipment, It will not remove the need for train protection, interlockings, communications, operational rules, or human supervision. It will not work perfectly everywhere, and it cannot be used safely without redundancy. Its real value is not in replacing the railway safety architecture, but in strengthening and modernizing it. The future of GNSS in rail is therefore not about satellites taking control of trains by themselves. It is about integrating satellite positioning into a wider railway ecosystem. If implemented correctly, GNSS could become one of the key enablers of the digital railway. It could make advanced signaling more affordable, improve how trains are monitored and managed, help railways use infrastructure more efficiently, and support future automation and moving block operation. With these insights, we hope we've covered some of the most important aspects of GNSS application. If we missed something, or if you think we got something wrong, feel free to let us know in the comments. Every comment, suggestion, and discussion means a lot to us and helps us improve our work and future videos. And finally, if you enjoyed this video, don't forget to subscribe to the channel and hit the notification bell so you never miss our next upload. If you'd like to support Railways Explained even further, you can do so through Patreon or PayPal, or by checking out our rail-themed merch and book. All links are waiting for you in the description below. Until the next video, stay on the right track.